Hi all, welcome to the lecture series on Aerospace Propulsion. Myself Manideep Gupta, Assistant Professor, Department of Aeronautical Engineering from MLR Institute of Technology. Today the topic which we are going to discuss is calculation of temperature of combustion. In the previous lecture we have gone through the heat of formation and calculation of heat of combustion. Okay, the energy liberated during the combustion. This lecture will give you how to calculate the temperature that is going to develop due to the heat release in the reaction. The temperature of combustion, how much temperature the products are going to attain after the reaction. Okay, so this is calculation of temperature of combustion. So coming to the overview of today's presentation, in this we will discuss the temperature of combustion, what is temperature of combustion, and we will discuss the procedure for calculating the temperature of combustion products. Okay, how to calculate this temperature of combustion, and the parameters affect the rocket performance. So these are the topic which we are going to discuss in this presentation, in this lecture. Coming to the temperature of combustion. What is temperature of combustion? Temperature of combustion is nothing but the temperature attained by the combustion products after the reaction. The temperature attained by the products after the reaction. Heat of combustion is nothing but the energy released after the reaction. Okay. So for example, consider the formation of steam. Formation of steam from the combustion of liquid hydrogen at a temperature of 20 Kelvin and liquid oxygen at a temperature of 80 Kelvin. So what is steam actually? Steam is nothing but the gaseous form of H2O. Steam is nothing but the gaseous form of H2O. So here we are going to find the temperature of steam after formation of H2O, right? From the combustion of liquid hydrogen. So how this steam is being generated? With the help of liquid hydrogen, liquid hydrogen, okay, at temperature 20 Kelvin, and the liquid oxygen plus liquid oxygen also in the liquid state, which is at 80 Kelvin, and it will form H2O. This is in gaseous state, so H2O steam, right? So here we will see this. Coming to the reaction of steam to produce steam in gaseous state. So 2 moles of hydrogen at a liquid state, are considering 2 moles of hydrogen at liquid state, and 1 mole of oxygen at liquid state at 80 Kelvin, and this is at 20 Kelvin, and H2O gas. H2O steam is formed, and we have to find the temperature of H2O. What is the temperature of H2O we have taken? 20 Kelvin. Temperature of oxygen is 80 Kelvin. We have to find the temperature of H2O after the reaction. I have to find TF here, right? So the path considered, how to find this temperature of combustion products. The path considered for determining the heat of combustion can be represented as, okay, represented as this equation. Okay, see here in this equation, TB means boiling temperature and TF means the final temperature of the steam formed. Okay, so first, what is the temperature of H2O? H2 at liquid. Okay, there are some first H2 hydrogen is at a liquid state at 20 Kelvin. So we have to bring down this hydrogen at liquid state to the gaseous state, right? So we'll bring the H2 from liquid to the boiling point. Okay, after that we have to change the phase of hydrogen from liquid state to gaseous state. We have to convert this hydrogen from liquid state to gaseous state at boiling point. After that, the hydrogen has to be bring to the STP condition. STP condition. Okay. Next, H2O also. H2O forms. Generally, we consider H2O is formed at STP condition. Product, right? It is formed. Consider it is formed at STP condition. After that, energy will be transferred to the H2O, right? So the liquid state hydrogen will go to that boiling point in the same liquid state. Okay, still the energy is there, then this liquid hydrogen will turn to gaseous water. Okay, that means steam. This water convert into gaseous state, that is steam. After that, at the boiling point, and next further the temperature increases to final temperature. The temperature increases to TF. Okay, so the path is like a H2 in liquid state at 20 Kelvin. So we have to bring down this H2 liquid to boiling point, which is also at liquid state. After that, we have to bring down this liquid hydrogen to, we have to convert this liquid hydrogen to gaseous hydrogen, which is okay. And here also TB, the temperature of the gas after conversion of state, temperature will be same, that is boiling point. After that, we will bring hydrogen to the gaseous state at STP condition. So the energy, if we can easily calculate the energy required, okay, to convert, to bring H2 liquid from 20 Kelvin to the TB is nothing but Cp delta T. Cp delta T, nothing but the change in enthalpy of the H2 liquid from 20 Kelvin to the TB. So we have to calculate Cp delta T here. After that, liquid to gaseous transition. So we have to calculate the latent heat of hydrogen, latent heat, that is nothing but energy. After that, we are bringing hydrogen gas from boiling point to the STP condition. So again, here again Cp into delta T. So this is nothing but energy 1, energy 2 and energy 3. The sum of these three energies will give you how much energy is required to bring this H2 liquid, H2 hydrogen at liquid state from 20 Kelvin to the hydrogen as gas at STP condition. Okay, this much amount of energy. How much energy is required? E1 plus E2 plus E3. This much energy transfer has to be taken place to bring H2 liquid to H2 gaseous state at STP condition. Right. The same happens even we have to calculate the heat transfer from here, that is Cp delta T. So how much energy is required to convert H2 liquid to the H2 liquid at boiling point, that is 100 degrees centigrade. After that, latent heat of vaporization, and next final temperature Cp delta Tf, boiling point to final temperature. And it's the same even we have to apply for oxygen also. Oxygen initially at 80 Kelvin, we have to bring oxygen to its boiling point. After that, liquid oxygen will convert to gaseous state. Okay, still if you decrease the energy temperature, then oxygen will convert liquid to gaseous state at same temperature at TB. And next, this gaseous oxygen has to be bring down to 298 Kelvin. So we have to find the energy transfer. So this is energy transfer 1, here the energy transfer 2, and this is energy transfer 3. 3 types, 3 transformation. We have to find the energies transfer. Energy is required to transform H2 liquid to the gas at 298 Kelvin. So we have to calculate all these energies, and if you sum, then we can understand how much energy is generated, and in that how much energy will is transferred to the how much temperature is being developed due to the energy transfer. Okay, so sometimes the temperature of the combustion products will be less than the STP condition. Sometimes the temperature of combustion products will be more than the STP condition. So the net heat balance relation for H2O liquid, H2O2 liquid and H2O gas is, right? What is the first one? So we have to convert, we have gone through the steps, right? H2O liquid. So Cp value, if you want to calculate the enthalpy, okay, enthalpy will change for different based upon the state of the liquid. If you take the hydrogen, the Cp value of hydrogen at gaseous state will be different, and Cp value of hydrogen, the same hydrogen in liquid state will be different. Okay, So while calculating the change in enthalpy, we have to consider the Cp according to the state of the substance. Okay. So here 2 moles of hydrogen, 1 mole of oxygen and 2 moles of H2O is there. So if I write the energy balance equation, okay, 2 moles of H2 liquid, right? 2 moles of H2 liquid. So we have to calculate Cp delta T, right? Delta, this is the delta T. Cp is in liquid state. Cp of H2 in liquid state. Okay. To the temperature. H2 liquid at 20 Kelvin. H2 liquid at 20 Kelvin. Next, this is conversion of oxygen to the boiling point, CpO2 in liquid state to a boiling point temperature. You can see from 20 to TB1. Here the temperature of oxygen is 80 Kelvin, 80 to boiling point of water. Okay. If you expand this equation, this will be 2 into Cp of H2 at liquid state into TB1 minus 20. Okay, this is nothing but Cp delta T of the H2 liquid, right? The same way, I have to bring down oxygen from 80 Kelvin. This is at 20 Kelvin, right? This is at 20 Kelvin. This is 80 Kelvin, and this is at normal STP condition. We have to increase the temperature. So 20. So I have to bring down. Okay, this H2O liquid is bring it to boiling point. This oxygen also bring it to boiling point. Okay, Cp delta T. And next, latent heat of hydrogen. Okay, latent heat of hydrogen to from liquid state to gaseous state. And next, latent heat of vaporization HV of the oxygen from liquid to gaseous state. Okay. After that, we are calculating the energy required for the hydrogen to bring from boiling point to the STP condition, and the same way for oxygen also from its boiling point to the STP condition. Okay. Plus next H2O. We have now we bought the H2O liquid. We bought H2O from liquid state to the STP condition, and oxygen also. We calculate the energy of for the oxygen from liquid state to the STP condition till this. Okay. Now this is for H2O. Okay. Now whatever the 2 moles of H2O formed, we consider that is at STP condition. So from STP condition to it will go to boiling point, right? So 298 to energy required to convert liquid liquid hydrogen to the boiling point. Okay. So liquid hydrogen liquid water at 298 Kelvin to the boiling point TB3 into Cp delta T plus latent heat of water. Okay, latent heat of H2O from liquid state to the gaseous state 2 moles, and next water from gaseous state Cp H2O in gaseous state to the final temperature Tf. Okay. So finally, this is the how many moles of water is formed? 2 moles. Okay, this is heat of formation of H2O, that equal to the heat of formation of H2O. Okay, here 2 moles formed, so we have considered 2 moles here. So if you balance this is the energy balance equation for formation of water from the hydrogen at 20 Kelvin and oxygen at 80 Kelvin. Okay, and here the TB1 means TB1, TB2, TB3 are the boiling temperatures of hydrogen, oxygen and water, and HV of H2 means evaporation of latent heat of evaporation for hydrogen, latent heat of evaporation for oxygen, and this is latent heat of evaporation for H2O in kilojoules per mole. So Cp represents the specific heat at kilojoules per mole, right? So the heat liberated in this reaction shown on the right hand side corresponding to the 2 moles of H2O, 1 mole of O2 and 2 moles of H2O. So the change in enthalpy can be assumed to rise the temperature of Tf. How much temperature is going to increase? That has to be find. That is nothing but Tf. Okay, if I write the equation for this, it will be if I expand this equation like 2 into CpH2 liquid state into delta T, that is Tb1 minus 20 plus this term Cp, one more Cp of O2 into delta T, boiling point of water, high oxygen minus 90 plus this term latent heat, 2 moles of hydrogen, latent heat of vaporization of hydrogen plus latent heat of oxygen Hv of O2 plus 2 moles of hydrogen from Tb1 to Cp of hydrogen gas, Cp of hydrogen in the gaseous state into delta T, Tb 298 minus Tb1, that is the boiling point of hydrogen, plus this term can be written as Cp of O2 in gaseous state delta T is 298 minus Tb2, 298 minus Tb2. What is Tb2? Tb2 is the boiling point of oxygen. So like this, if I expand all these terms, then you will get the final, okay, final value of Tf. Okay, final value of temperature of the combustion product, that is Tf. Next, there is a general procedure for calculating the temperature of combustion products for propellant combination, for any propellant combination. So this is a formula, basic formula, like heat of combustion is delta Hc is equal to minus of sum of heat of formation of the products minus sum of heat of formation of the reactants. So number of moles of this is number of moles of products and this is number of moles of reactants. Okay, even we have to find the products. Suppose hydrogen is there, oxygen is there, hydrogen plus oxygen will give you, it will give you H2O, but how many moles of H2O is going to form, that will be decided based upon the amount of oxygen provided and amount of hydrogen provided. Okay, based upon the hydrogen and oxygen content, the product sometimes changes. Okay, if the oxygen is more, hydrogen, whatever the available hydrogen, that will convert to H2O, and still you will get some extra oxygen as a product, combustion product, right? So whatever the energy liberated, suppose 286 kilojoules is generated for 1 mole, this 286 kilojoules will also transfer to the oxygen which is in the products also. Okay, this 86 kilojoules will transfer to the product H2O and also the available O2 in the system. So the final temperature will affect in this reaction. Suppose oxygen is less. Suppose less oxygen is provided when compared to the hydrogen. So what happens? H2 plus O2. Okay, 2 moles of hydrogen plus 1 mole of oxygen. Okay, I will say 3 moles of hydrogen. Okay, 1 mole of O2. How much? What is the combustion products here? 3 moles of hydrogen is there, but only 2 atoms of oxygen. So 2 moles of H2O will form plus 1 mole of H2 will be as it is. Okay, whatever the 2 moles of energy liberated, the 286 for 1 mole, right? In 2 into 286 kilojoules of energy, this energy will transfer to the water molecule, 2 moles of water, and also transfer to the hydrogen. And this water vapor and hydrogen both has to come to equilibrium temperature. Okay, both will go to the final temperature Tf. Then the temperature obtained by the H2O will be different. The first case, the temperature of water steam is different. The final temperature of steam will be different. The second case, the temperature of steam will be different. Depends upon the products forms, other products forms. So that's why it is very, very important to find out whether it is a stoichiometric reaction or oxidizer is more or fuel is more. Based upon that, we have to find the products first. After that, we have to find the temperature of combustion products. Okay. For surplus of oxidizer, the mixture ratio will be more than stoichiometric mixture ratio. So, completely oxidized products of combustion can be assumed to be formed. Suppose, example, CO2 forms with a C carbon, okay, and H2O forms from hydrogen. So, for the oxidizer less than that required for complete combustion, then mixture ratio is less than the stoichiometric ratio. Okay, oxidizer is less. That means it is called fuel rich. So, under oxidizer products will form. Like instead of CO2 formation, sometimes carbon monoxide will form. Okay, carbon plus O2 has to give CO2. Okay, but I will take 2 moles of oxygen, okay, and 3 moles of carbon. Then the products will not be like this. Okay, the products will not be like this. Okay, carbon monoxide will form. First, 3 carbons will form 3 carbon monoxides. Okay, so how many carbons will left? Out of 4, only 1 oxygen will be left because 3 oxygen is used here. Next, 1 CO2 plus 2 CO will be the combustion products. For this, 1 CO2 plus 2 carbon monoxide will be formed. So it is an underoxidized product. If you provide less oxygen, okay, carbon atoms are 3 moles, but oxygen has to be 3 moles. But we supplied only 2 moles here. So underoxidized product like carbon monoxide will form. Okay, let us see how this reaction happens at different conditions, oxidizer rich conditions, like a fuel rich conditions and stoichiometric reaction. The products form will be different. That we are going to discuss now. So in most cases, what we prefer is a fuel rich propellant. We prefer fuel rich propellants in most cases. So coming to this, the procedure to find the products form. What are the different types of products forms when we provide fuel rich propellant comprising carbon, hydrogen and nitrogen. So how the reaction happens will be explained now. We are considering the fuel rich propellants here. Okay, and this propellant consists carbons, hydrogen and nitrogen. This has to react with oxygen. So which one react first? Either carbon reacts with oxygen, hydrogen reacts with oxygen, or nitrogen reacts with oxygen. How this reaction happens will be discussed now. So first step is whatever the nitrogens, first carbon, hydrogen, nitrogen is there, but first nitrogen will react. Okay, the nitrogen will react and all the nitrogen in the propellant is assumed to form N2. Okay, and the products of hydrogen is formed to H2O. Okay, first all nitrogen atoms forms assumed to form nitrogen molecules and products, and all hydrogen is assumed to form H2O. Okay, next the oxygen is left in the propellant after forming of H2O. Even still some oxygen is left after formation of H2O, then the oxygen will go and react with carbon and forms carbon monoxide. First carbon monoxide, directly it does not form carbon dioxide. First it forms carbon monoxide. If still oxygen is left, then carbon monoxide react with another oxygen atom and forms CO2. Okay. Next, if the amount of oxygen is not sufficient to convert the hydrogen into H2O, only part of the hydrogen will be converted to H2O and the balance will be left as H2. Okay. Next, carbons in the propellant remain as carbon in the products, because oxygen is not even sufficient to convert hydrogen into water. So it will some of the oxygen will react with hydrogen and forms H2O, and the remaining hydrogen will be as it is, and carbon will also be as it is if oxygen is not sufficient. The method does not take into account the breakup of dissociation of the combustion products at high temperatures and formation of oxides of nitrogen. So this method will not be applicable for high temperatures. Okay, it will not consider the dissociation that happens at high temperatures. So now we'll take some examples. Now we'll consider some examples and discuss how the combustion products forms at different conditions like oxidizer rich and all the fuel rich and stoichiometric. So first we consider a chemical reaction between the kerosene. Kerosene formula is C12H24. C12H24 we are considering the kerosene, and oxygen is O2. So let us assume a stoichiometric reaction between kerosene. That means kerosene is completely burned with oxygen and there is no oxygen left. Both are in appropriate proportion. So stoichiometric reaction. First, the reaction will be C12H24, 1 mole of kerosene atom. If it reacts with 18 moles of, if you supply 18 moles of oxygen, then it will form 12 moles of carbon dioxide and 12 moles of H2O. Okay, the stoichiometric mixture ratio. Okay, the stoichiometric mixture ratio is, see here, 18 into 32. This is for oxygen. Oxidizer to fuel, and this is the for kerosene. Okay, you will get 3:3.43. 3.43 is the stoichiometric mixture ratio. So if the mixture ratio is less than the stoichiometric, then it is oxidizer. So stoichiometric mixture ratio for kerosene and oxygen is how much? 3.43. So what we are taking here is, we consider the mixture ratio greater than the stoichiometric mixture ratio, that is 3.43. So let us assume some random mixture ratio greater than 3.43, then it will be automatically oxidizer rich. Okay, so I am considering the mixture ratio is 3.81. Okay, 3.81. Okay, so then the number of moles of oxygen to be provided for 1 mole of kerosene has to be found. Okay, so you know the equation for mixture ratio. So mixture ratio is 3.81, has to substitute here number of moles of oxygen into atomic mass, number of like 1 mole of kerosene already we considered, the kerosene is 168. So number of moles we don't know, you have to get it. So if you solve this, you will get number of moles of oxygen to be provided for a mixture ratio of 3.81 is 20 moles of oxygen to be provided. Okay, suppose if you want to go for oxidizer rich, okay, this is an oxidizer rich mixture ratio, right? So now we will write the equation with 20 moles of oxygen and 1 mole of kerosene. These are the combustion products that are going to form. So what, according to the procedure, first what happens here, if you see here, how many carbon atoms are there in this? 12 carbon atoms. Okay, carbon atoms are 12 carbon atoms, and hydrogen atoms. How many hydrogen atoms? 24 hydrogen atoms are there. And oxygen, how many oxygens are? 20 into 2, 40 oxygen atoms are there. Okay, according to the procedure, how the products are going to form, first what happens, whatever if there is nitrogen, it will form nitrogen atoms, it will form N2. Okay, but no nitrogen atoms in this reactant, so nitrogen will not form. Okay, next, whatever, first hydrogen will react with oxygen and forms H2O. Okay, how many hydrogen atoms are there? 24 hydrogen atoms. Okay, 24 hydrogen atoms react with oxygen and has to form H2O. How many moles of H2O will form? 12 moles. 12 into 2, 24, right? So it will form 12 moles of H2O. Okay, let us I will write this equation here. 12 moles of H2O will form. Okay, according to the procedure, first hydrogen has to react with oxygen and forms 12 moles of hydrogen. How many hydrogens are left? Hydrogens left are 0. All hydrogens are burned. Okay, used. How many oxygens are used to form H2O? 12 into O. So 12 minus 12. How many oxygens are left? 8 and 2. 28 oxygen atoms are left. Still 28 oxygen atoms are left. So next step, after formation of H2O, next oxygen, whatever the oxygen left, that has to go and react with carbon to form carbon monoxide. Okay, how many carbon atoms are there here? How many carbon atoms are there? 12 carbon atoms. So 12 carbon monoxide will form first. Okay, 12 carbon monoxide is formed. Okay, so how many oxygens are used? 12 carbons are used here. So carbons left is 0 and here 12 oxygens are used. So minus 12 oxygen. How many oxygens are left? 6. Okay, 6 and 1. 16 oxygens are 16. Still 16 oxygen atoms are left, right? So according to the procedure, whatever the carbon monoxide, that will go and react with oxygen atoms remaining and forms carbon dioxide. So how many carbon monoxides are there? 12 carbon monoxide. So how many oxygen atoms required to form CO2? 12 oxygen atoms required. So if you go with so then 12 COs will convert to 12 CO2. So 12 oxygens will be minus, and how many oxygens are left? 16 minus 12, 4 oxygens are left. So this 4 oxygens will be like as 2O2. Okay, see here 12 CO 12 okay, 12 CO2 is formed, 12 H2O is formed, and 2 moles of O2 is formed. This is how these products are formed according to the procedure. Okay, now you might be understood very clearly how these products are formed. If you provide 3.81 mixture, if you make 3.81 mixture ratio. Okay. Now we go for fuel rich mixture ratio. Now the same happen, how the products are formed if they had a fuel rich mixture ratio. What is the stoichiometric? 3.43. So if the mixture ratio is less than the stoichiometric mixture ratio, then it is called fuel rich. And the fuel is more, then the fuel is more, oxygen is less. Okay. So it should be less than 3.43. So we will just consider 3.05 mixture ratio. Let us consider the mixture ratio 3.05, and we have calculated the number of moles of oxygen atoms required to maintain 3.05. So number of moles of oxygen we don't know. So NO2 into atomic mass of oxygen is 32 and kerosene is 168. So it should be equal to 3.05 our mixture ratio. Then you will get number of moles of oxygen required is 16. Okay. So if the write the reaction, okay, C12H24 plus 16 moles of oxygen. Okay. In this case, how many? So C12H24 plus 16 moles of oxygen, and we have to find the reaction, right? Okay. How many more carbon atoms are there? 12 carbon atoms. Hydrogen atoms 24. And oxygen, how many? 16 into 2. 32 oxygen atoms are there. Okay. Hydrogen atoms are 24, carbon 12, and oxygen atoms are 32. We have to find the resultant equation. Okay. Here, first hydrogen atoms will react with oxygen and form water molecules. Okay. Let us say H2O is formed. How many moles of H2O can be formed? 12 moles of H2O will form. Okay. So this hydrogen becomes 0. How many oxygen atoms are burned? 12 oxygen atoms minus 12. How many are left? 20 oxygens are left. Now this carbon go and react with oxygen and forms carbon monoxide. Carbon monoxide. How many carbon atoms are there? 12 carbon atoms. So we have 20 oxygen atoms. So easily we can form 12 carbon monoxide. How many oxygens are burned? 12 oxygens are burned. So still 8 oxygens are left. How many oxygens are left? 8 oxygens are 8 oxygen atoms are left. Okay. So in these 8 oxygen atoms, these 8 oxygen atoms go and react with carbon monoxide, this carbon monoxide, and has to form carbon dioxide. But here we have 12 carbon monoxide atoms, but here we have only 8 carbon oxygen atoms. So how many carbon dioxides can be formed? So 8 oxygen go and react with 8 carbon monoxide and forms, okay, these 8 oxygen atoms will go and react with carbon monoxide and forms 8 CO2. Okay. How many carbon monoxide are left? 12 minus 8, still 4 carbon monoxide will be as it is. Okay. So this is how the reaction, 12 H2O, 8 moles of carbon monoxide and 4 moles of carbon monoxide, because there is no 4 atom. If there is 4 oxygen atoms are there, suppose 4 atoms are there, then 4 oxygen atoms go and react with carbon monoxide and forms 4 CO2, but oxygen atoms are not available. That's why this carbon monoxide will be as it is. Okay. See, 12 H2O, 8 CO2 and 4 CO. This is these are the outcomes you will get. These are the combustion products if you maintain fuel rich mixture ratio. So whatever the energy liberated, suppose some X kilojoules energy is liberated here, this X kilojoules of energy will transfer to the H2O, it will transfer to the CO2, and it will also transfer to the carbon monoxide. The temperature of H2O rises, CO2 rises, and also carbon monoxide rises, and finally you will get a temperature, that is TF. So this TF depends upon the heat absorption capacity of H2O, CO2 and CO. Each because H2O heat absorption capacity will be different, specific heat will be different, CO2 specific heat will be different, CO specific heat will be different. Okay. So that's why H2O may take more energy, CO2 may take some less energy compared to based upon the specific heats. This temperature will be different. The final temperature will change, depends upon this mixture ratio. Okay. So this is about the reaction for fuel rich mixture ratio. So like this, we have to find the first combustion products. After that, we can go for heat of formation of all these products. Then we will get the final temperature of the combustion products. Okay. And if you see the graph here, the temperature of combustion products is increasing as the mixture ratio value is increasing up to stoichiometric. The temperature of combustion product is increasing. After stoichiometric mixture ratio, the temperature of combustion products is again decreasing. So it is better if you maintain a stoichiometric mixture ratio, the temperature of combustion products will be maximum, and even sometimes, but it is not exactly at stoichiometric mixture ratio, but here you will get the peak. That means just before the stoichiometric mixture ratio, and it should be in the fuel rich region. Then you will get maximum temperature of combustion. Next, performance parameter that affects the rocket. Okay. So coming to the basic characteristic velocity we have gone through in the nozzles, that is C star is equal to 1 by tau into under root of R naught into Tc by m. Okay. See here. So it is a gas constant, universal gas constant, temperature of combustion. Okay. That means in the combustion chamber temperature and molar mass of the gases. Okay. And this is gamma. So specific heat ratio should be less, and its temperature of combustion product should be more for maximum C star, and molecular mass of the combustion product should be less to get maximum C star. Okay. So C star value is higher as the temperature Tc increases and the molar mass of the gas is reduces. Next, C star is weakly dependent on specific heat ratio. It also depends on gamma, but the dependence of the C star on the gamma is less. In order to obtain lower molecular mass of the combustion gases, so if the molecular mass is less, you will get maximum C star. How you will get a lower molecular mass combustion products? So in order to get the lower molecular mass of combustion gases, the propellant needs to be based on elements having low atomic mass. Whatever the propellant, here we have taken C12H24. What are the elements of this propellant? Kerosene, carbon and hydrogen. Okay, this carbon and hydrogen atomic mass should be, the elements of the propellant should be less, low atomic mass. Then automatically the combustion products are also, the atomic mass will be, molecular mass will be less, and you will get maximum C star. So this is about the temperature of combustion and procedure for calculating the temperature of combustion products and the performance that affect the rocket parameters. Okay, so today this is the summary of today's lecture. Thank you.